Hello and welcome students. Today we are going to discuss a new topic of solid state, that is packing efficiency. Students, as you know, in case of solids, constituent particles are always closely packed. But even after the close packing, some voids or free spaces are always there. You can understand this with the help of diagram. For example, this is a unit cell containing 4 constituent particles. But even after the close packing of these 4 constituent particles, some free spaces, these are the free spaces or voids which are present in this solid. Now, the total percentage which is covered by these constituent particles is called packing efficiency. For example, if I say 74% part of this unit cell is covered by these 4 constituent particles and remaining 26% part is covered by the voids, these voids, then the packing efficiency for this solid would be 74%. So we can define the packing efficiency as percentage of total space filled by the particles. Today we will learn how to calculate the packing efficiency in case of FCC, BCC and simple cubic lattice. So let's start with the FCC. Packing efficiency in case of FCC, HCP and CCP would be same. HCP means hexagonal close packing, CCP means cubic close packing and FCC means face centered cubic. To calculate the packing efficiency in case of FCC, first I'll make the diagram. Suppose this is a unit cell for FCC where particles are present at the corner as well as at the face center. In these particles which are present at the corner and at the face center are in touch with each other. Now I'll give the name to each corner: A, B, C, D, E, F, G, H. Students, this AC is the face diagonal which is equal to B, and edge length for each edge is equal to A. So this AB is equal to A and BC is also equal to A. The edge length would be same for each edge. Students, now you can see here in the triangle ABC, according to Pythagoras theorem, AC square is equal to AB square plus BC square. AB and BC both are the edges, so A square plus A square is equal to 2A square. AC is the face diagonal which is equal to small b, so B square is equal to 2A square and we can write it B is equal to under root 2A. Students, now you can see here in the diagram that is this face diagonal B is equal to 4r. Length of face diagonal length of this face diagonal B is equal to 4r, where r is the radius of the sphere. You can see here, this is the r, this is 2r, and this is again r. So total value of this face diagonal is equal to this 4r. So we can write it B is equal to under root 2a is equal to 4r. So A is equal to 4r by under root 2, or we can write it A is equal to 2 under root 2r. Students, now we will put the value of this A in the formula of packing efficiency. Formula for the packing efficiency is equal volume occupied by 4 spheres in the unit cell upon total volume of the unit cell. Volume occupied by 4 spheres in the unit cell upon total volume of unit cell into 100%. As you know, number of atoms per unit cell for FCC is equal 4. That's why we have used 4 spheres in this formula. When we calculate the packing efficiency for BCC, we will use 2 spheres in place of this 4 spheres at that time, and in case of simple cubic lattice we will use 1 spheres, because number of particles per unit cell in case of BCC is equal to 2, and number of atoms per unit cell for simple cubic lattice is 1. So we have used 4 spheres in unit cell in this formula. Now, as you know, volume of 1 sphere is equal to 4 by 3 pi r cube. So volume of 4 spheres would be equal to 4 into 4 by 3 pi r cube upon total volume of the unit cell would be equal to a cube, and we have calculated the value of a here 2 under root 2r. So it would be equal to 2 under root 2r cube into 100%. Students, it would come 74%. So packing efficiency in case of FCC, HCP and CCP is equal to 74%, and it is always fixed. Now we calculate the packing efficiency in case of BCC. To calculate the packing efficiency in case of BCC, first I will make the diagram of unit cell for the BCC. This is the diagram of a unit cell of BCC, and you can see here in the diagram the constituent particles are present at the corners as well as at the body center, and these particles are in touch with each other. Now I'll give the name to each corner. A, B, C, D, E, F, G, H. This AF is the body diagonal, and this FD is the face diagonal. These are the edge, and the edge length is equal to A. Edge length for the each edge is equal to A. The value of this body diagonal, we can assume it is C, and suppose this face diagonal is equal to B. Now we can say here in the triangle EFD, in triangle EFD, according to Pythagoras theorem, B square is equal to A square plus A square. Now it is equal to 2A square, or we can say B is equal to under root 2A. In the same manner, we can calculate it for the triangle AFD. In triangle AFD, C square is equal to B square plus A square. C square is equal to B square plus A square, and as we have seen earlier that B square is equal to 2A square plus A square, so we can say C is equal to 3A square, or it is equal to C square is equal to 3A square, or C is equal to under root 3A. Students, here B is equal to this face diagonal and C is equal to this body diagonal. Now the length of this body diagonal C length of body diagonal C is equal to 4R, where R is the radius of the sphere or radius of the atom. Suppose radius of this atom is equal to R, this is 2R, here it is R. So the radius of these spheres would be equal to 4R. So we can say here C is equal to 4R is equal to under root 3A. So we can say here A is equal to 4R by under root 3. Students, now we will use the formula of the packing efficiency as we used in the earlier case in case of FCC. So the formula of the packing efficiency is equal to volume occupied by 2 spheres in the unit cell. Earlier we used the formula 4 spheres in the unit cell. Here we know that in case of BCC, the number of constituent particles in one unit cell is equal to 2. So formula would be volume occupied by 2 spheres in unit cell by total volume of the unit cell into 100%. Students, as we know, the volume of one sphere is equal to 4 by 3 pi r cube. So volume of two sphere would be equal to 2 into 4 by 3 pi r cube. In the total volume of the unit cell would be equal to A cube, and the value of A is this. So the volume of total volume of unit cell would be equal to 4R by under root 3 cube. Students, if you put the value of this pi over here, because R cube will be cancelled, this value would be 68%, and it is always fixed. So the packing efficiency in case of body centered cubic unit cell or body centered cubic lattice is equal to 68%, which is somewhat less as compared to FCC. The reason is clear, because in FCC the number of constituent particle was 4, so the packing efficiency was more. Now we will calculate the packing efficiency in case of simple cubic lattice, or we can say primitive unit cell. For this, first I will make the diagram of the unit cell. Suppose this is a primitive unit cell or simple cubic lattice. In this you can see here, if the edge length is equal to A and radius of the sphere is equal to R, then we can see here A means edge length of this unit cell is equal to 2R. R plus R is equal to 2R. Now we can put the value of this A is equal to 2R directly in the formula of the packing efficiency, because to apply the formula of the packing efficiency we only require the value of A. So we can see here the value of A can be calculated directly, so formula can be used directly here. Packing efficiency in case of simple cubic lattice is equal to volume occupied by one sphere in unit cell upon total volume of the unit cell. Into 100%. As we know, the constituent particles or atoms in primitive unit cell or simple cubic lattice is equal to 1. So we have used here 1. So volume occupied by one sphere in the unit cell is equal to 4 by 3 pi r cube. As we know, the volume of the sphere is equal to 4 by 3 pi r cube. In total volume of the unit cell is equal to A cube. And the value of A is equal to 2R. So it is equal to 2R cube into 100% is equal. If you solve this, you would find it is equal to pi by 6 into 100%, which is equal to 52.36%, or roughly we can say it is equal to 52.4%. So you can remember any of these two values for the packing efficiency in case of simple cubic lattice or primitive unit cell. So students, we have completed this topic, packing efficiency. In this topic we have seen the packing efficiency is maximum in case of FCC, that is 74%, followed by in BCC, that is 68%, followed by simple cubic lattice, that is 52.36% or 52.4%. Next topic I will cover in the next video. Thank you.